Hello everyone, I'm Hao He, currently a PhD candidate at Peking University. I'm going to present this paper, Multimetric Ranking Approach for Library Migration Recommendations. It is a joint work between our lab and Software Analysis Lab at Huawei Technologies, and my advisor is Minghui. Nowadays, the availability of package hosting platforms such as Maven, npm, and PyPI makes releasing an open source library much easier. As a result, the number of available third-party library is exponentially growing in the recent decade, with tens of thousands of new libraries appearing each year. For example, the number of Maven artifacts have risen from about 50,000 in 2014 to more than 350,000 in 2021. However, third-party libraries are prone to all kinds of failures, such as security vulnerabilities, lack of maintenance, license incompatibilities, and misalignment with project requirements. Under such circumstances, a project often has to replace one of its library to another library with similar functionalities, which we call library migration. For example, a Java web application may be using its org.json in its RESTful API module for communicating with its front-end interface. But maybe one day the developers recognize that the license of org.json is problematic, or the library itself lacks important features. Then they have to replace this library. But they may be not sure which library is the best one to migrate to because there are many other choices, such as JSON, Jackson, or FastJSON. Choosing the best library to migrate can be difficult, mostly because subjective information is lacking on the internet. Most online resources that compares different libraries are opinion-based posts or discussions, which may be outdated, biased, or not trustworthy. Meanwhile, developers make migration decisions based on prior experience. For open source projects, core developers may open issues and discuss about migration possibilities until they reach a consensus. However, there is no guarantee that their opinion is correct and their choice is optimal. It is also possible that some developers may miss some migration opportunities which may cause problems in the future, or their project may miss the benefits brought by the new libraries. Things may even be worse if the developers of a project have only limited expertise. We believe things will be better if we can have an approach that automatically recovers information from existing high-quality software repositories and summarizes how they have previously conducted migrations. This information can serve as a reference for other practitioners when they need to replace their libraries. Therefore, we define a recommendation problem as follows. The input is a library query specified by a user. The output is a list of recommended libraries in which the user can migrate from the specified library to one of the recommendations. The recommendations should be made based on evidence from existing software repositories. For example, if a user types the name org.json::json in the search box, an approach should automatically returns the relevant libraries and tells you how it makes decisions from existing repositories. There are several existing approaches in this direction, and they follow similar procedures. First, these approaches mine library changes from project revision histories, which can be commits or releases. For example, suppose the project has 6 commits, and shown in this figure, they compute which library is added and which library is removed in each revision or each commit by analyzing project dependency configuration files. For example, in revision 5, library A is removed and library F is added. Given such data, they collect target libraries for migration using different predefined metrics and consider a library as an eligible migration target if and only if its metric exceeds a given threshold. In their approaches, different metrics are considered to capture both library change frequencies and code change frequencies, and they are designed to consider both changes in the same revision and across multiple revisions. However, their approaches have either low precision or low recall depending on its filtering thresholds, which limits their usefulness in practice. We propose to improve the performance of existing approaches in the following two directions. The first direction is to use multiple metrics that capture evidence from multiple sources, such as library changes, commit messages, source code changes, and commit topology. The second direction is to rank the results of each library query by relative values. As shown in this figure drawn from ground truth data and false positive data, a global filtering threshold will either filter out many true positives or keeps many false positives, and thus hard to reach a performance balance. The first metric we propose is rule support, which captures information from library changes. The intuition is that the frequently added libraries with the removal of library A in the same commit are likely to be replaced in A. It is defined as rule count AB divides the maximum rule count that starts from library A, in which rule count RC is the number of times library A is removed and library B is added in the same commit. For example, for the three projects on the right, rule count AF equals 2 because the commit R5 in the first project and commit R3 in the second project have removed A and added F. Similarly, rule count AE equals 1 because the commit R4 in the third project have removed A and added E. Since the maximum rule count that starts from A is rule count AF, which equals 2, rule support AE will be 1 divided 2, which is 0.5. The second metric we propose is message support, which captures evidence from developer-written commit messages. Such information serves as a direct evidence of library migration. It is defined as the logarithm of message count MC plus 1, which counts and MC counts the number of commits with commit messages stating a migration. For example, MC org.json will be incremented by 1 if we discover a commit message like the one here, stating things like replace something from or other. We implement such detection by keyword matching. The third metric we propose is API support, which captures evidence from code changes. The intuition is that code changes that removes API references of A and add API references of B in the same hunk may be indicating a migration. It is defined in a similar form compared with rule support, in which API count AC is defined as the number of hunks that we can observe API changes from library A to library B. For example, if we discover a hunk like that in the right, the API count AC of org.json will be incremented by 1. Finally, we propose distance support, which is intended to capture evidence from commit topology. The first intuition is that the previous metrics may miss migrations that span over multiple commits, and we want to capture this. The second intuition is that migrations are unlikely to span over a large number of commits. Therefore, we define distance support as the mean of reversed commit distance as follows, in which ref AB is the set of relevant revision pairs that added and removed library A and library B, and this RIRJ is the distance metric. More details can be found in the paper. Given the proposed metrics, our approach computes the confidence value using a simple multiplication of all the metrics. We found that a simple multiplication works surprisingly well enough and can avoid overfitting compared with machine learning-based approaches. The reasons may be that the ground truth data is sparse, as we will mention later, and we only have 4 metrics. Given a library A, our approach will mine candidate library set from a large number of software repositories and compute the confidence value for each candidate library. Then it will return the candidates ranked by the confidence value and the relevant migration commits as defined by message count MC. We implement our approach for about 20,000 Java GitHub projects and 180,000 libraries hosted in Maven Central. We collect both the library data and software repository data from various sources, implement a data collection and processing pipeline, and also implement a website for demonstration and user interaction. All source code and data have been released on GitHub, and the tool can be accessed in the provided link. For more implementation details, please refer to our paper. To evaluate our approach, we need to construct a ground truth dataset. For performance evaluation, we recover and update the ground truth dataset in the existing work using a systematic validation and extension procedure. As an additional contribution, we also validate the results of our approach using 480 most popular libraries not included in the aforementioned dataset, and we get a new migration dataset. The two datasets can be used to facilitate further research, and we will use the first dataset to evaluate the performance of our approach. We use the following performance measures to evaluate the performance of our approach: MRR, top K precision, top K NDCG, and top K recall. They are all common performance measures in information retrieval to evaluate the performance of ranking problems, and they all ranges from 0 to 1, the higher the better. We compare our approach with both approaches from existing work and other alternatives using only some of the proposed metrics. We can see from the table that our approach outperforms existing approaches and reaches a balance between precision and recall. Some filtering-based approaches may achieve higher precision with some parameter settings, but their recall will be low in these cases. On the other hand, our approach can achieve the highest recall of 0.89 while maintaining a high precision of 0.79. Therefore, we conclude to the best of our knowledge that our approach achieves the best performance in this problem domain. Finally, we show two recommendation examples. The first example is org.json, which has been mentioned several times before. It is a simple JSON library and also the reference implementation of JSON specification in Java. However, compared with other competitors, it has less features and an unusual license term. The software shall be used for good, not evil, which causes legal problems for many industry projects and makes it incompatible with many other licenses, including Apache 2.0. Therefore, many migrations can be found from org.json to other JSON libraries in recent years. In the results of our approach, all top 8 results are correct migration targets, and our approach can return a diverse set of JSON libraries for user choice, and the ranking position is identical to the popularity of migration. Our approach can also correctly identify relevant migration targets for each relevant migration commits for each target library. The second example is C3P0, a database polling library since 2006. The group ID of this library has been changed once, and many other competitors have emerged in recent years. The first recommendation results occurs because of the group artifact ID change. The second recommendation result is Hikari CP, which features its high performance and lightweight. The results colored in gray are false positives. The fifth result is Alibaba Druid, a database polling library designed for monitoring purposes. And the seventh result is C3P0 for integrated use with Hibernate. We can see that migration data is very sparse in this case because even the second ranking library only has one migration commit. Even if the data is sparse in this case, our approach still identifies most of the frequently migrated targets and the correct migration commits. Our approach still has several limitations which can be improved in better designed approaches. For example, our approach will fail if a compatible library exists but no projects have done a migration. Also, important problems still remains in the topic of library migration, and we can list some of the interesting problems as examples here. We believe they can be explored in future research. To summarize, we make the following contributions in this paper. First, choosing the best library to migrate can be difficult, so we formulate a problem of migration recommendation. Second, we propose a new multimetric ranking approach for the mind migration recommendations. Third, to the best of our knowledge, our approach achieves the best overall performance in this problem domain. Feel free to ask any questions, and thank you for your attention.